Hi everybody, I'm Abdul Ragab and this is very science V question and answer, and the contents are about these topics STA and CDC and Asic and very conditional design, and this topic today is about static time analysis. The question today, he gives you this design and asking you without changing logic stage and with minimum added area allow this circuit to operate at 20 MHz clock frequency. Let's see how we can do that. First, we're gonna check if we apply 20 MHz to the circuit, can make any violations. Let's see for setup violation. First step, we're gonna calculate the clock period from clock frequency, which is equal 1 over clock frequency equal to 15 nanoseconds. And for setup, we're gonna apply for setup equations. We gather this combinational logic and apply them into these equations. We're gonna find out that this values is not less than 15 nanoseconds, so there will be setup violation. Solve this violation and allows the circuit to work at 20 MHz clock frequency and 50 nanosecond clock periods. We're gonna apply pipeline techniques. Pipeline techniques is by adding these registers between these paths, by breaking up this critical path, by adding these flip-flops, and we change this critical path into 3 passes. And let's check if this 3 passes have any variations and they can operate at 20 MHz clock frequency. For first pass from flip-flop 1 to flip-flop 2, by applying combination logic into setup equations, we're gonna find out that 20 is less than 50, so there is no setup variation for first pass. And second pass from flip-flop 2 to flip-flop 3, by applying the combinational delay, which is equal 40 nanoseconds, will be less than 15 nanoseconds, so there's no setup variation in this pass. And third pass, which is equal 3 combination clock from flip-flop 3 to flip-flop 4, and by applying this combination delay into the setup equations, we're gonna find out that 40 less than 15 nanoseconds, so there's no setup variation. So by applying techniques, we can allow the circuit to work at 20 MHz clock frequency. The second question today, he gives you this design and asks you how we can solve these violations. This design combines of 2 paths. The first path has setup violation with setup slack equal to -1 nanosecond, and second path has plenty of setup slack equal to +3 nanoseconds. To solve this violation in the first pass, we're gonna try to minimize the delay of the combinational logic by moving this inverter to the right and this flip-flop to the left. And let's see how that can help me to solve this violation. For first pass, setup slack equal to -1 nanosecond as it appears in the design, and we need this setup slack to equal to 0 nanosecond. So as I said before, we're gonna move this inverter to the right and this flip-flop to the left, so we minimize the logical delay to get the new setup slack equal to 0 nanosecond. So the first path has no violation. Let's see what about the second path. For second path, it has plenty of setup slack equal to +3 nanoseconds. If we add to this path the inverter delay, we're gonna find out that the positive slack will be minimized to equal to +2 nanoseconds. So there's no setup variation in this path, and we call this moving registers retiming, and this helps me to solve setup variation in this path. But you can see that hold time wasn't mentioned in this problem, so you need to be careful in real design that when you do retiming for this path, it may be cause hold variation, so you need to be careful about the hold time when you do retiming. The third question, what if after manufacturing you find out that there is a hold variation or setup variation? Which one will be the worst one? How can you deal with it? For setup variation, it's easy to solve by decreasing the clock frequency, but for hold variation, it's difficult to solve. So we always say that hold variation is more dangerous than setup variation, so you need to be careful about hold variation more than setup variation. That's all for me today. If you have any feedback or questions, please leave a comment. And thank you